let's talk about heat transfer. So one thing that you need to get straight in your head when thinking about the way that we think about heat in terms of science is that heat is what moves, not cold. So we're transferring heat whenever something's getting hot or cold. It's a transfer of the heat. It's not a transfer of cold. Basically, cold is the absence of heat. So in doing these types of discussions, you have to define a few things. The one thing of very importance to define is your system. So just for the sake of this discussion here, I'm just going to say it's a box. So we'll go ahead and call that our system. And the system is defined as the thing of interest. Everything else in the universe is the surroundings. So there's two ways to talk about this, is whether or not heat is going into the system or going out of the system. So with that in mind, we like to use the letter Q for heat, and we'll use that to talk about the direction in which heat is moving. All right, so suppose we had some situation where heat was going into the system. So heat is going that way. If you were to define a numerical quantity for Q for the system, do you think it would be positive or negative if you're putting heat into it? It should be positive. Heat is going to be increasing. So we can say that Q is greater than 0. These types of processes are defined as being endothermic, literally meaning going into the system. All right. So suppose you were holding something in your hand that was undergoing an endothermic process. What would you feel? Would you feel as the object was getting hotter or colder? But is your hand? So we're defining the object in our hand as the system. Your hand itself is the surroundings. It'll feel cold, yes. So if your hand is acting as a surrounding and the system is taking the heat from it, that means the surroundings are going to get colder and the system in here is going to increase in heat. But what we actually observe is the opposite because we're part of the surroundings. So it's really confusing here to keep track of the signs. That's why it's really clear that you're defining what your system is. So once again, if you're holding an object in your hand that's undergoing an endothermic process, you're going to feel cold because your hand is the surroundings. Heat's going to be lost from your hand. All right. The other process is if heat is coming out of the system. So if we're looking at the total heat in the system, it's the opposite. Q is less than 0, meaning it's negative. Let me go ahead and be clear on the signs here. This sign would be positive. This sign would be negative. We define these types of processes as being exothermic. So the same analogy again, if you were holding an object in your hand that was undergoing an exothermic process, what would you feel? Your hand would get hot. Yes. The way that I always kept this straight in my head when I was a student was any combustion reaction, meaning you're burning something, is an exothermic process, meaning it's going to give off heat. In the case of combustion, it's literally giving off flame. So use that to remember what an exothermic process is. But what's happening to the system when you have an exothermic process? It's getting colder. Okay. So in this particular topic here, one of the things you're going to have to be able to do is you'll be told some kind of process and you'll be asked whether or not it is an exo or endothermic process. So the best example I like to think of is, what about if you're freezing a glass of water? So suppose you took some water out of the tap, put it in your fridge, and it'll freeze over time. So we're going to say that the surroundings around it is the body of our freezer. So that'll be our surroundings. So here we have our freezer, and we are defining the water itself as our system. So everything such as the glass, everything else, your packs of meat and veggies and all that are in there, those are all your surroundings. All right, so you leave it in there overnight, you come back in the morning, it's frozen. Was that an endo or exothermic process? Think about it in terms of what's happening up here. It's exothermic, yes. So when you freeze your water, the heat is going to draw to the outside here. That means the temperature in here is going to go down. Over time, the temperature in your freezer may go up. That's why we have the systems in place there to pull the heat out of your freezer. All right. So when doing these kinds of problems, make sure that you are clearly identifying what is your system. So next problem here I'm going to do is a little ambiguous in this regard. So you got to make sure that you're clear in identifying your system. All right, the next example here is sweat evaporating. Basically what we have here is we have our skin, and then we have like a little bead of sweat here. Let's try it both ways. So there's two possibilities here. One is the sweat is a system. If you were being given a question like this, I would go ahead and define this as system, because that's the actual word used here. So let's go ahead and say that this is our system, and our skin is the surroundings as well as the air around your skin. All right, so if something is evaporating, what's happening to the temperature? It's going up. So does that mean that heat is going into it or out of it if temperature is going up? Into it. So we say that Q is greater than 0, meaning that it's endothermic. I just write endo dot there for short. And temperature is going up to the point where it just evaporates off. And what do you think is happening to the skin here? It's going to end up getting a net cooling, right? So basically what's happening here when sweat evaporates is that it's taking heat from your skin, pushing that into the sweat. It evaporates to get a net cooling effect on your body. If it were the reverse, you'd actually be heating up as sweat evaporated, and that wouldn't be pleasant. So definitely make sure that you're clear on what the system is. If we call skin the system, that is exo or endo. It's exo. It's losing heat. You're cooling off. All right, good.